Okay, so today is the last lecture. So I'm going to talk about the conformal block a little bit, and then the last part talk about the conformal bootstrap slightly. Okay, so last time, so we tried to consider the 4-point function, and then we encounter the situation that we need to consider conformal block, and then so that the important fact is that the conformal block. So this one is conformal block. So if you consider this kind of conformal block, only depends on the delta 1, 2, which is delta 1 minus delta 2, or delta 2, 3, delta, 3, 4. 3, 4, 3 minus delta 4. So this one is a fact. I mean, there's a way to derive it. I don't think I have time to. I mean, this one is coming from the so-called conformal Casimir equation. And also, there's lots of ways to derive this one. But so at this moment, you can accept as a fact. So that's why I wrote this one. It's the delta 1, 2 upon delta 3, 4. Okay. And then when everything, so at the end of the last lecture, so Dolan Osborne's contribution is amazing in this high-dimensional CFT. So if everything is scalar, and then del I is the same, then G 0, 0. So 0, 0 means the difference is 0. And 0. LO is 0, LO is 0, UB is something like a hypergeometric series, U delta O over 2, and a hypergeometric series. I'm not going to write down everything, so M factorial, and then so U to the M, 1 minus B to the M, and then so this kind of happens a chunk series. You can read. Okay, and then today I'm going to talk about the slightly special setting. So we set the x1 to be in this flat space. So this is the d-dimensional. So therefore, this is the SD minus 1 dimensional sphere, and I put the x as the x1. Yeah, x1 is here. x1 is r times e to the I alpha, and then x2 is minus r times e to the I alpha, and I put the x3 to be 1, x4 to be 1, and x3 to be minus 1. Okay, so this kind of situation I consider. So in the case of the cylindrical spacetime, so we have we put the theory on so the O1 here, O2 here, and then here after that, I put the O3 here, O4 here, like this. Okay, so this is the situation I consider. And then I call it this x1 is equal to rho r times e to the I alpha. So this is the kind of situation I consider. Okay, so then so see that this conformal block 4-point function can be decomposed as follows: O n vacuum or 3 or 4 O and N and E to the step minus delta O plus N tau epsilon. So now Euclidean, I consider Euclidean safety. So R cross SD minus 1 Euclid CFD. Euclidean CFD. So now for the time transition like this way, and then O and then O1, O2, and then back like this way. Okay, so that's the case I consider. So here O is a primary field. O here in the middle is here insertion is the primary field, and this is the level of the sentence. So we consider this kind of situation. Okay. And in particular, so this one can be written as the following way. So what is it? And in this case, so yeah, I have to mention that so U is equal to 16 rho to the square, 1 plus rho to the 4. So and B is equal to 1 minus rho. So this is a cross ratio. In this setup, the U and B are like this. Okay, U and B are like this way. However, it's easier to write down the following. So it's easier to write down. So R is this direction. This is this direction. Tau epsilon, tau Euclidean is this one. So R is related to E to the minus tau E. Okay, so that's the situation we consider. Okay, in this situation, so one can just consider this conformal block written here in these. So the conformal block is in fact, it can be written as follows: the G delta O and LO. Oh, delta, okay, so delta and L, and the delta 1, 2, delta 2, 3, can be written as follows. The vacuum or 3 or 4, and then delta and then L, mu1, mu L, and then here, and also you consider delta L, or 1, or 2, and then okay. So this contribution. So if you consider that in the middle of channel is this compound dimension delta and the spin L, then so you need to sandwich by this algorithm. So here, and then we assume this one both are the symmetric, again, traceless, spin L or rank L answer. Rank L answer. Rank L. Like this one. And then here you can consider, so this contribution can be understood as the following: something times constant times So here I have to put this one. E to the minus delta O plus L tau E. So constant times symmetric and 1 mu 1 and L mu L. So that's the case. I mean, if you consider the sphere, and you put the O into the in one direction, O1, and then O2 is the completely opposite direction. This is S3 minus 1 sphere. Okay. So now, so it's only, of course, so here you can consider just the unit sphere at this in cylindrical coordinate. So therefore, it only depends on the unit vector where this operator sits, and since it's a Rankel symmetric traceless tensor, so you have to put like this. This is only consistent with the transformation of the Lorentz transformation, and so therefore this one is also true. So therefore this is actually constant times symmetric. But now you need to take up the inner product and 2 mu 1 and 2 stars and this is animal, so and 2 and mu L like this. So and 2 is the at this point O3 and O4 just pointing something like this, right? O3 and then O4 like this. Or maybe I think it's better to put the z-axis. That's more. This is O3 and O4. So this is energy. You can. Okay. And then some constant times e to the minus delta O plus L tau E. So this is the expression. So therefore, if you take a contraction between these two, this will become something like this, right? Constant times e to the minus delta plus L tau E, and then some function of alpha and 1 and 2. Which is this one is actually cosine alpha. Alpha is this direction. Alpha is this direction. So this is very familiar with what you learn in the quantum mechanics, in spherical harmonics and so on. Okay. For instance, here. In the case of d equal to 3, in the case of d equal to 3, so this is the S2, and it's in z-axis, in O3 and O4 z-axis. So therefore, if you consider the, say, vacuum O3, and then say spin L delta L. So this is essentially the proportion of the constant times the L and M equal to 0. Okay. It's a spin L, but in Z rotation it's invariant, right? So therefore it should be how to say, there are no JZ angular momentum. So LZ, okay, LZ angular momentum L and is N L. And since it's invariant under the Z rotation, this should be 0. So on the other hand, if you consider this one, O1, O2, and delta L, so now it's treated by alpha. So therefore, this should be e to the I alpha LZ N LX or whatever. I mean, it's without lots of generality. It can be wherever direction. I don't know, maybe X. So X, and then L, and M equal to 0. So this is the, and you just take the inner product. If you take like this alpha L X, L M equal to 0, and L is equal to M equal to 0, like this way. So this is what you know by spherical harmonics, like this way, times constant. And this is called Legendre, so some constant. This is called Legendre. So in general, so this function A, so in D equal to 3, this function is in fact the Legendre polynomial. For arbitrary dimension, it's generalized to what it's called. I don't know that. And D equal to 4 is become D equal to 4 is called Chebyshev polynomial. Chebyshev polynomial. Arbitrary dimension is called what is it called? It's called the Gegenbauer polynomial. This is the first time that I heard this polynomial Gegenbauer polynomial for arbitrary dimension. It's called. Anyway, so the detail is not important, but the important thing is that it's like a higher dimensional version of spherical harmonics appear when you consider it, when you put that operator in this form, and in this form, in the internal channel, when the internal channel is this symmetric traceless tensor. So that's what's going to. Okay, so another important coordinate we can consider from now on is the x1 to be 0, x3 to be 1, and x4 to be infinity, and so on. So when you consider the dimension, so x1 to be 1, 0, 0, like this way, x2 to be y1, y2, 0, 0, like this way, and x3 to be 1, 0, 8, so this should be 0. And x4 to be infinity, infinity, 0, 0, like this way. So if you put like this way, and set z to be y1 plus I y2. So this is the convenient choice of coordinate of 4-point function. Convenient choice of 4-point function. So then the cross ratio will become u is equal to z squared, and b is equal to 1 minus z squared. And yes, this case. I mean, so always this conformal transformation can map to this. Previously, x1 is equal to rho, x2 is equal to minus rho, and x3 to be minus 1, x4 to be 1. Okay. Previously, we put like this way on the cylindrical coordinate. And then this can be mapped to the like this. Okay. So in this case, the relation between z and rho can be obtained as follows. So z and rho can be obtained, and the relation with z is equal to by 4 rho, 1 plus rho square. Actually, this become important, so I need to keep it. So let me write down here. Later, it will become important. Z square, b is equal to 1 minus z square, and then z is equal to 4 rho. Like this. Okay. Okay, those are relation between z and rho. And then maybe I think I erased the wrong position. And then last time, at the end of the last lecture, I told you that if there is a pole, the position of pole in the conformal block will show that the presence of some singular vector. Okay. So that's exactly what's happening. So if you consider the conformal block G, delta L, delta 1, 2, delta 3, 4, R and alpha is as before. This is R is equal to e to the I alpha. Okay, and then what you get is that there's a pole. There's a pole of the RA minus delta A star. And then G, delta S, LSA, and delta 1, 2, delta 3, 4, and the R. It behaves like this here, or the delta is close to delta S star. Okay. So if you consider the OPE of this O1 and O2, and if you have the O as the conformal dimension delta A star, which has the singular vector in the conformal family, then if delta A, so maybe delta is equal to delta A star, which has the conformal family, let's see, delta operator A, and if you consider conformal family, at some point you encounter OA as singular vector, and you have to get rid of to get the unitary theory. So around this, when delta goes to this the conformal dimension for particular operator OA, which contains the singular vector in its conformal family, it behaves like this. So that's the property of conformal block. And in fact, so if you write down as follows, so if you write down the H, if you factor R alpha, 4R minus delta G delta L R alpha. If you write down like this way, so you just factor out this R to the minus delta, which always appears as the overall factor, or the overall factor. You just factor out this factor, then this And this control block will take this function will take the recursion relation as I mentioned last time. Our alpha is equal to h infinity and then L R alpha plus sum of delta minus delta S star R A and then sorry, I don't think I have time place. So plus sum of A delta minus delta S star H delta S star plus NA and L A star S and then R. This kind of so the notation is that so this singular vector appear in level n A. So if you ask the P mu1 total P mu and A, and then times on operator OA, this contains this kind of contains the singular vector OS singular vector like this as a linear combination. So that's the meaning of NA here, and then it has a spin. So this has a spin LAS. Okay, that's the case. And then the reason why the it's called recursion relation is that if you know the order of, so it's a function of R, as I mentioned, it's a function of R here, and then function, so e to the minus tau e is equal to R. Okay, so the alpha is a function of R and alpha. Function of R and alpha. And if function of R is, if you understand the operator is the same, capital N, so this will determine the order of R to N plus NA. So if you use this formula, so if you know the function of this function h in terms of the function R to the n as a polynomial, and then this will multiply R to the NA, and that will give you higher order function R. So that's why. So this is called recursion relation. So if you use this structure when the conformal block takes a fall, so this is called recursion relation of conformal. Okay. So that's the case, and then those function is determined. So those functions are already determined by in some way. So this is determined by conformal Casimir equation, and also. So this RA is some constant. This is constant is written in terms of delta 1, 2 and delta 3, 4. This constant is also well understood, and I'm not going to write down the expression. So this, as I mentioned, so the singular vector has 3 types: 1, 2, 3, and I don't remember the detail. This one is P square acts on the operator. N times, and then we have how to say this kind of sigma 1 T sigma L or L1. Sigma 1 to sigma L. This kind of notation. And the other thing, I don't remember the detail. I think type 2 is P axon number of times O, and the T axon number of times. It splits like this way. The other is P dot T acts on this one, T. So times K or something. So in the, I don't know how many lectures ago, like 3 or 4 lectures ago, we classified like 3 types of singular vector appear by using the index-free notation. And we found that this kind of classification. Unfortunately, I didn't print out this part, so I maybe, this is very schematic, but you can take a look back the my lecture note. So in section, I don't remember. Anyway, so number 1, number 2, number 3, you can just determine how the R look like. R and A, R2 and A, R3 and A. So you can write down the expression is known by people. Coase and so on, Simon Duffy and so on. So these expression is, I'm going to write down in given in 11.33 of my lecture. The expression is known. So you can just, for the, when they, I think this is the case when they, yeah. Okay, so that's the, what's really happening in the. So I'm not going to write down. So the expression is kind of like, again, hypergeometric series type. Hypergeometric series type. Geometric series expression type. So, okay. And the important thing is that it's a function of delta 1, 2, 1 minus delta 2, and delta 3, 4, delta 3 minus delta 4. So it's a function of these variables. That's also, I should mention. Okay, so that's the one property of the conformal block. So the other important property is that the so the other important property is some kind of polynomiality. So this plays a very important role in conformal bootstrap. So other important property of the conformal problem. So this is one the property the recursion conformal block satisfied. That's the recursion relation. Other property is the so often did I write that one? Okay. Yeah. Did I write? Yeah, so here, so as you can easily see, so if you write down the expression in terms of U and B, so U and B are cross ratio, can be written in Z function Z. So the most important, the convenient place to do the expansion is 1/2. And the Z bar is also 1/2. This is the convenient place to do the expansion. This is always to the conformal bootstrap people. Looking at convenient place for convergence. conversions of the conformal block. Because I mean, as I mentioned, so the Donald-Osmond expression, so is n, and a bunch of expression u to the n, b, 1 minus b to the n, 1 minus b to the n. This kind of expression appear in the conformal block. So this is a hypergeometric series, blah blah n, and so on. And if you plug this one into here, when z is equal to 1/2, it's really, how to say, when n and m are increasing, so there's a positive number, natural number or something like that, then it's really conversion. So this is the most convenient place to do the expansion for conformal block. And then, so if you add to these conformal blocks, delta L, z equal to 1/2 equal to z bar, and before that you act the derivative of z and z bar in m times n times like this way. Then this in fact has a following form: r star to the delta, and then p l n delta. And L N like this. So this kind of so R star is in fact the when you set Z and is equal to 1/2, so R star is something like rho of Z equal to 1/2 and take absolute value. So you just take 1/2 inside of here. So then what was that? So this 1/2 divided by 1 plus square root 1/2 square. This is the R star. Okay, so this is the overall factor you always have when you have a conformal block at the internal channel is delta. And the important thing is that this ratio, the leading order of R, is something like is written in terms of the conformal dimension internal channel. So this internal channel here. So I call it this one's internal channel. And then, so the denominator can be written as a product of the delta minus delta A star. A is 1, 2, 3. And then, like this. So it's a product of the singular vector. So this, so when the singular vector up here, and then NA is a less than capital. Okay. So this means that the operator O A has a singular vector OA S up to, so this number is NA is less than capital A. That's my notation. Less than or equal to capital after. So the singular vector appear in a conformal family after level capital A. Okay. So it can be written like this way. And for unitary theory, so this is always, sorry, this denominator is Q. Denominator is Q. This is always positive. Positive for unitary CFT. Okay. That's the case. Unitary CFT. And then also important property is this guy is polynomial in delta. So this is the important property we're going to use for the conformal block later. Actually, polynomial in the delta, the degree is known, so degree of degree is equal to degree Q delta n plus n plus n. So that's fine. So that's what's really happening. So this is an important property. We will use it later. Because of the, for the sake of time, I'm going to skip this conformal customer equation. I mean, as I mentioned, so the leading order when delta goes to infinity case, delta goes to infinity, internal channel infinity case. So this constant part can be determined by conformal customer equation. Anyway, essentially the rough idea is that the if you have the conformal customer equation is that the so in core group is the SO D plus 1, comma 1, and then if there is a customer relation MAB, which is given by maybe 1/2. It's a quarter customer C2, I call it. Is something like 1/2 J mu nu minus D squared minus 1/2 J mu plus D mu, like this way. And this can act on the conformal block. So the C2 can act on conformal block G delta L, delta 1, 2, delta 2, 3. 3, 4 of Z and Z bar acts as the so the conformal block becomes the in fact the eigenfunction of this Casimir operator. So this one is some kind of differential operator, acts as a differential operator, operator. It's like a, I mean, L mu can be written like a X mu del mu minus X mu del mu. You can write down like this way for whatever, for quantum mechanics and so on. So you can write down this action Casimir operator on the other differential operator acts on conformal block. That will give you some. That will become the eigenfunction. Delta 1, 2, delta 3, 4, and so on. And this value is already known as the delta minus D plus L plus D minus D. So this is formula. Eigenvalue is this one. Yeah. So this is set for the second order. So this function also satisfies this very similar equation. And if you take delta goes to infinite limit, one can easily determine this function by solving this differential equation and so on. Which I'm going to omit in this because for the sake of time being. and I'm going to talk about the conformal bootstrap based on these properties. Yeah, sorry. I mean, because of for the sake of time, so this is the last lecture. I need to be a little bit schematic instead of going to detail. But just, I mean, I mentioned all the property the conformal block satisfies. One is the recursion relation coming from singular vector. Okay. And then the other is some polynomiality. So this, if you act on derivative with respect to z, it satisfies this kind of property when you set z equal to 1/2. Using this one can say many things actually for OPE and so on by using conformal bootstrap. Okay, so then I'm going to talk about what are the conformal bootstrap. And the idea is very simple. Idea is really like even like appeared before I was born, like more than 50 years. That polygon in the competence. So the conformal bootstrap, as I mentioned many times, is the so essentially, so even fuse like O1, sorry, O2, O3, maybe I should write the O3, O4, and then delta O is equal to O1, O4, O2, O3, O prime, and delta O prime, L O prime. Okay, like this. So this is the schematic idea. I'm going to talk at the level equation wise. You can write down like this way: delta sum of O C1 to O C3 for O G delta O L O Z bar Z bar. Oh, sorry, this is 4. Like this way. Like this. Yeah, I think I should write down like this. Okay. Okay, so that's the equation. You can. So as you recall, so this U is in fact something like x12 squared, x34 squared divided by x13 squared, x24 squared. Whereas this B is the x14 squared, x23 squared, so and then x13 squared, x24 squared. Like this way. So therefore, if you exchange like how to say 2 and 4, so this is exchange like a 2 and 4. So if you exchange 2 and 4, you bring it to this case. If you exchange 2 and 4, you go back to this case. Okay. So therefore, if you exchange 2 and 4, so U become B, B become U. Okay? So therefore, if one is depends on Z, the other should depend on 1 minus C. Okay. So that's the case. That's the mean. So so this is crossing, sometimes called crossing symmetry. So these two are related by crossing symmetry. Exchange on this crossing symmetry. And then people just write down this equation. It's very simple equation, but it's hard to solve. As follows. So suppose, so from now on, I call O1 equal to O2 equal to O3 equal to O4 is the isomodal spin sigma. So or scalar, some scalar operator. If all the operators same. So in the case, so we'll consider such a special cases. In that case, in this case, this Conformal bootstrap equation become like this way: sum of C sigma sigma O square F delta sigma down O LO C bar is equal to 0. The operator O or the operator F down sigma down O LO C bar is equal to 1 minus C square delta sigma G00 delta O LO C bar minus C 2 times delta sigma and then G00 and delta O LO minus C. Okay, so this becomes the, I mean, you just said the 1, 2, 3, 4 are the all same, and then, yeah, you just write down the equation. So this is called Conformal bootstrap equation. Conformal bootstrap. So this is called Conformal bootstrap. And we want to solve, and we would like to understand what's the meaning of this Conformal bootstrap equation. Okay. For consequence of this. Okay, so let's see the one consequence of this Conformal bootstrap equation. Hopefully I can. Okay. So one thing one can do is that they just extract this Conformal bootstrap equation. So then from extract identity operator, extract. Well, O is identity operator. It's just bucket from this Conformal bootstrap equation. So if you do that, you will get the following thing. So C sigma sigma 1 square, and then 1 minus C so the sign is not identity. C, and then C sigma sigma psi square, and then one minus C 2 sigma rho of V of delta sigma, okay, of delta sigma psi, and then V 2 sigma delta sigma rho 1 minus V, like this. So here I use a part of the this one G delta psi of the 0 of C bar is proportional to if the dependence is rho times the delta, is that if you take the absolute if you put that properly into the appropriate position and looking at only Z dependence, it only depends on rho times of Z times delta psi. So that's the dependence you will get. So as I mentioned, so this conformal block G delta L whatever R alpha is the dependence is the sum over n. Okay, so A L cos alpha and R times delta. So that's the dependence of the conformal block in the international delta and L. And if you put the alpha to be 0, or you can just if you put that properly the alpha, this function becomes 0. Not 0. If it is 0, it's not convenient. Some constant. Okay. Some constant. And you can, if you only look at the R dependence, your R is always dependent on delta to psi. So international. So therefore you can just put like this. Like this. Okay, and the rho of Z is given here. Rho of Z is given here. Okay, and then so you just expand the when Z is around very small, when set the Z is equal to 1/2 and plus X. You just put the Z equal to 1/2 and the X is very small. You just put the V is equal to 1/2 and X is very small. And do the expansion for left hand side. Left hand side is easy to be done. So if you just put the left hand side with this assumption, you will get the following. So some number times X plus 4/3 delta sigma minus 1 delta sigma 2 times delta sigma minus 1 x cubed plus all that x to 5. So one can just write down. And suppose the okay, and now let's look at this part. Let's look at this part. Suppose the delta psi. So here, so d is equal to 1/2, almost 1/2. So therefore, this part is 1/2 become to the 2 to the delta, and this one is also become 1/2 2 to the delta 2 to the delta sigma. So therefore, you can just break these dependence out of it. Okay. So these are become overall factor. because we put the z equal to 1/2. Okay. And what's left is that here this becomes some number, 2 to the 1/2, 2 to the delta sigma rho of z, delta psi, minus rho of 1 minus z, delta psi, become like this. Okay. Okay. And unfortunately, I made a typo in my lecture notes. I guess I made a typo, or I'm not sure if I corrected. Let me check. Yeah, it's not corrected. Let me correct now. The psi. Okay. So this one, if you assume the delta psi is bigger than suppose, let's see. So what is psi? Psi is just if you take the OP of sigma contain psi, right? Psi like this way. Okay. And suppose this conformal dimension of psi is very big. It's very big. So let's consider it's not bounded very big by delta sigma. Suppose like this. So then this function can be approximated. So this function can be approximated as follows. This function can be approximated in terms of x is some number times x plus 4 over 3, and then delta sigma squared x cubed plus 4 to the x to the 5, like this. So it's very similar to the left hand side. It's just x and x cubed and x to the 5 and all x to the 5. And you can compare between these two under this assumption. Okay? Under this assumption. Under this assumption, and it just compares. So let's call this one as some constant sharp 1 and sharp 2, and then compare between these two. So this means that the minus sharp 1 times c sigma 1 square is equal to sharp 2 sum of psi, which is not identity, and then c sigma psi square like this. Okay. Do you agree with that? Is it okay? So this is the first order of x. If you compare the first order of x, the x to the cube case, so what you get is sharp 1, c sigma 1 square. And now you have a 4 over 3, delta sigma minus 1, 2 delta sigma minus 1. So that's the quotient of x cubed in left hand side. And if you look at this part, what you get is as follows. Sorry, this is psi. Sorry, psi. So what you get is psi 2 and the 4 over 3 sum of c sigma psi square and delta psi square, and psi is not equal to. Okay, so that's the equation you would get. Fine. Okay. And suppose there is some, if you take the OP and then OP and like this way, so this means that so it's bounded. There's a conformal dimension of delta, and let's say that this is delta sigma, and delta mean it's bounded by below. So which means that the psi needs to be lower bound is like this way, and you have like psi 1, delta psi 2, and so on. So it's a lower bound is here, but it's bounded from below. So this is the assumption. Okay. So then just solve this one so that you encounter some inconsistency. Let's see. So for the sake of convenience, what you get is that the minus square is delta min C sigma sigma 1 square is number 2 delta min, okay, sum of psi is not equal to 1 C sigma sigma psi square, okay, psi square. And then if you compare between these two, you encounter that delta square psi, delta psi square is always bigger than square. Delta means square. So therefore it's bounded by this guy. Number 2, sum of C sigma sigma psi square delta psi square psi is not equal to 1. Okay. So here delta mean is always less than delta psi. Okay. Therefore this inequality holds. And if you use this one, of course you don't have this. You don't need this for third. And this is equal to minus sharp 1 square C sigma sigma 1 square, and then delta sigma minus 1 to delta sigma minus 1. Okay, like this. Okay, so and then again, you just factor out this minus 1 sharp square. I don't like this. There is no square here. So. And compare between these two. So this means that the delta mean square is less than delta sigma minus 1. Delta sigma, 2 times delta sigma minus 1. Okay? So this is the case. Okay? And then take a square root. Let's take a square root, naive square root. Okay? So delta mean, okay, is somehow is less than this one. But this breaks the assumption of this one. So here I assume this delta mean is far less than the delta sigma. This breaks the assumption. So there's a contradiction. So there's a contradiction. So therefore, so if you do the OP calculation, conformal dimensions that appear if you take OPE of sigma and sigma, this conformal bootstrap equation written here. Conformal bootstrap equation tells us there must be upper bound. There must be upper bound. So the situation cannot be like this way. It has to be something like that. So this is not true. This is not true. So if you have a delta and delta sigma, I don't know what's going to happen, but it has to be bounded below something body, and then it's something like this. Delta psi. It's bounded below. Bounded from above. It should be bounded above. There is some upper bound. It's called in Chinese. It's called I don't know, 上升. Is it correct? 上升. Yeah, like this. It has to be. So this so therefore, if you solve this conformal bootstrap equation simply, this will give you some constraints on the conformal dimension OP. Okay. So this is very naive analysis. Okay. And we only solve this z equal to 1/2 and z equal to 1/2 and expand by x in around the x 1/2. Okay. So this is the constraints from the conformal bootstrap equation. Okay. And if you, but this is very naive analysis. But if you can use the many things to improve this bound actually. So you can consider more descendants more rigorously, and also you set these equal to somewhere else, or you can just consider the somewhere z is not 1/2, or you can consider some other 4-point function. So here I assume this O1, O2, O3, O4 or some scalar operator or sigma, but we can consider something different, right? Yeah. So the psi can be some primary field, and maybe sigma psi. If psi is the primary operator, you can consider this kind of 4-point function. Whether this will give you some other information by solving this conformal bootstrap equation. Okay. So in this way, one can just consider what's going to happen when you take OPE, what are the conformal dimension, and so on. One can just give you some constraints on the using this conformal bootstrap. Okay. So this is the flavor of this how we use conformal bootstrap equation. Okay. So let's take a break, and after like 10 or 15 minutes, I will switch to the slides. And there's some important progress has been done by more than decades ago by people solving this conformal bootstrap equation, solving this. Okay, using this conformal bootstrap equation, and then to solve 3D isomorph. So this one, because of the computation is really heavy, so I use I create a slide. So last like 1 hour is I'm going to use slides to explain using this one how to solve the 3D isomorph after the break. Okay, let's take a break. Yeah, and if you have a question, just let me know. Hmm? I thought it's working. Mhm. What's going on? It was working just before. Before the class, I checked the errors. Somewhat. Hmm? Not good. Wait. What? Okay. Yeah. Wait. Maybe it's better to reboot. Or isn't you to send the PDF file to here? Oh, maybe like this. Uh, what? Oh, it works. Okay, good, good, good. Maybe I can send that. Oops. it's not working just before. You cannot. Okay, someone it's not working. So it doesn't work. 为什么？那没办法。It was working just before. Huh? How can I send? E? E. Oh, good. Wonderful. Good. Okay, now it's working. Why mine? Anyway, okay. No. Is there any full screen mode? I don't know how to do this full screen, but anyway, it works. It's kind of annoying. Why it doesn't work? Hey. Okay. Okay, let's get started the second half. So I wanted to talk about these like mainly so these two papers made a how to say milestone in the solving. People like there are many people. Elshock, Paulus, Holland, Richkoff, Simon Duffy, E.G. and so on. And Tyler is solving 3D Ising model with Conformal Bootstrap. So, as I mentioned, 1944, Onsager solved the 2D Ising model. And right after that, there is some optimism that even 3D and so on, 3D Ising model can be solved exactly. But many people have tried, but no success. And the people realize that 2D and 3D are very different, somewhat. But even before this this is a paper appeared in 2012. Even before 2012, computer simulation, they can use the Monte Carlo simulation to understand what's going on in 3D IC model. And they realized that they can the 3D IC model at the critical temperature can be obtained by just can have a conformal symmetry. And then they determine critical exponent, which is the conformal dimension of the critical exponent is just delta E and delta sigma, as you know, in IC model, by using Monte Carlo simulation and so on. But here, this paper try to determine this delta E and delta sigma by using conformal bootstrap equation. So those two papers I'm going to explain. The first one, so as I mentioned in the first half of the lecture, or the first half, so you can use this conformal bootstrap equation to give a constraints on these conformal, the OPE quotient, OPE, and also conformal dimension. So we assume the sigma cross sigma is somehow epsilon, contain epsilon, and then the main hope is that using conformal bootstrap to give some bound for delta. To do that, so their paper use so-called sema to give us some constraint on conformal dimension. They use so-called semi-definite programming. So that's the semi-definite is some real symmetry matrix Y, which satisfy this property for any vector C. Okay. In the case of 2x2 matrix, necessary and sufficient condition for semi-definiteness is the Y11 and Y22 are non-negative, and the determinant is positive. Okay, so that's the condition, sufficient necessary condition for semi-definite for 2x2 matrix. And the problem. So okay, so I should title this semi-definite programming problem. The problem is to consider some variable yi, and then positive semi-definite matrix Y, and they just keep some constraint. So this satisfies this capital Y and small y satisfy this kind of constraint, and the A is some matrix, and the B is some constant, and C is also some constant, and so these constraints are indexed by A, and under this condition, and then minimize B times Y. B is some given vector B. So this is called semi-definite programming problem. Okay, this is kind of like a given matrix or vector. So B, A, capital B, small c, and small b. Even though those matrix and constant minimize this value under constraints of this one. And we assume Y is always semi-positive definite, Okay, and Y can take any value as long as it remains semi-definite. So let's consider the simplest example for this setting. Let's suppose A is small a is this index is 1, 2, 3, and I is 1, 2. So then the capital A matrix is 2 by 2 is given by like this way, and the capital B is given here, C is given this kind of constant. Then, if you solve this constraint, it really means that the Y should take this value. If you just solve this equation, Y should take this kind of value. And we need to, and we want to minimize the small b is the 1 and 2. So then y1 plus 2y2 is the, we try to minimize this pattern. Okay. You can see that it's not too small, right? You can see it. Okay, and we need to solve that this capital Y is semi-definite. So therefore, semi-definite, if you take a determinant, it should be positive, which means this value should be, this y1 square plus y2 square is less than or equal to 1. Okay? And this is very easy to solve. And what is the minimize y1 and y2 is that you can easily, next. So the constraint is this y1 and y2 are inside of this inside of with this, and the y1 plus y2 constant lines like this blue line. And try to minimize just bring this into this point that's tangent to this disk, and then that is the minimizing point. So that's a very simplest example for this semi-definite programming problem. Okay. Let's try to apply this semi-definite programming problem to the conformal bootstrap. So as I mentioned, especially in the 3D model, as I mentioned, so this is a conformal bootstrap equation. This is a conformal bootstrap equation, and we can again take a derivative with respect to z and z bar, and expand around the z is equal to z bar. Okay. So you can consider this kind of quantity. Just apply this number of derivative in the conformal bootstrap equation. Okay. And then extract identity operator, as I did in the previous in the first half of lecture. And the conformal bootstrap equation become like this. Okay. Conformal bootstrap equation become like this. Okay, and suppose there is some alpha mn. There is suppose alpha mn, which satisfies two conditions. These two conditions. Then you cannot solve this conformal bootstrap equation. Okay, because if you do that, the important thing is that maybe it's okay. Important thing is that the left-hand side is something like, if you just add the minus c, sigma 1 square, sum of alpha mn, and then f, what was that? It's 0, 0, 0, 0 delta sigma mn, and m and n. If this quantity is positive, this left-hand side, so this quantity is positive. This means that the left-hand side is negative. So this quantity should be negative. On the other hand, if you look at the right-hand side of this equation, conformal bootstrap equation, so if you just do that mn alpha mn delta sigma delta psi l psi is not assigned. mn, and the sum of psi is not identity. Psi is not identity. Okay, psi is not identity. Then this should be positive. Okay, this should be positive. Right hand side should be positive, but left hand side is negative. If there exists alpha satisfying this condition, you cannot solve the conformal bootstrap equation. So which means that there is no solution for conformal bootstrap. Okay, that's the case. So given that, so changing delta and so on, if there is changing delta and so on, if you can find such alpha, which means that you cannot solve conformal bootstrap equation. So those conformal dimensions will be excluded from the bootstrap equation. Okay. So such a conformal data will be excluded from unitary CFT. So that's the case. So that's the okay. And then translate this problem into the semi-definite programming problem. Is that to do that we will do the following. As I mentioned, if you expand the conformal works with derivative. So as I mentioned, so there's f delta sigma delta operator LMN is just a derivative acts on N, derivative z bar acts on N, and the original conformal block O and LO, and then set the z is equal to 1/2 and z bar is equal to 1. Okay, this one can take the following form. So this will take some number r to the r star to the delta O times 4 or something, and the polynomial divided by q, right? Q sigma O, sigma O, and then this is Mn and L, like this. And here I use a different notation. So this chi of L is this denominator. So it's just chi of L is denominator. 1 over Q is chi of L here. Okay. And as I mentioned, so this denominator is always positive for unitary CFT. Okay, unitary CFT. And then this PL, so the numerator here is polynomial in delta, as I mentioned. So this is a property of the this conformal block. Okay, and then so the question is whether you can find the alpha Mn such that this satisfies these conditions satisfied. If this is the case, you cannot solve the conformal bootstrap equation. So therefore, this means that this delta will be excluded. So therefore, here I just said that exclude some minimum value of this internal channel conformal dimension delta, which satisfies this one. Then, which means delta mean is actually excluded from conformal bootstrap equation. Okay. And here is the fact that any polynomial P. So this is, as I mentioned, this P is the polynomial in conformal dimension delta. Okay. So therefore, this polynomial can be just write down in terms of this kind of inner product, where N and B are semi-definite metrics. Okay. Here is the trying to connect this conformal bootstrap problem to the semi-definite problem. So therefore, this alpha Mn times PL, so the alpha Mn PLN is a polynomial on delta, polynomial on delta, and polynomial on X. So therefore, one can just write down by using this Hilbert theorem, you can write down like this way, using the semi-definite metrics. Okay. And if you expand this equation by in terms of XL to the K, then you use XL, and you look at the degree K, and the equation becomes like this. The equation becomes like this. Okay. So the problem is the AL and BL are the semi-definite metrics, and under this condition, try to minimize minus alpha Mn this value, and so that's the semi-definite problem we encounter. So in the previous example of this one, in the previous example, so alpha Mn is corresponding to yi, and then am I correct? Sorry. Yes. Well, alpha Mn is yi, and then P Mn L of K corresponding to BAI, and then AK and BK here corresponding to AN and then AL and BL corresponding to Y in the previous slide. So this is the correspondence. So the correspondence in upstairs, the problem is, so these constraints in here, if you use this dictionary, one can just move to the this conformal bootstrap equation. I mean, it's it's a conformal bootstrap equation. So it's using Hilbert's theorem, this PL is a polynomial. One can write down like this way using semi-definite polynomial, semi-definite matrix A and B, and try to minimize this value. Okay. In this way, if you can just find this kind of solution, and then this is actually if it is positive for any alpha Mn, so you cannot solve the bootstrap equation. So that's how they solve. Try to give an upper bound for this delta mean. Okay, and one can. I mean, they use the computer. They create a computer program and they use the numerical analysis, and this is the result. Here, this vertical axis is the energy, conformal energy density operator, and the horizontal is the spin. Conformal is the spin operator, and then this white region is excluded by this solving this conformal bootstrap equation with this semi-dependent program. So all those if there exists CFT, okay, with these two primary operators, and solve the conformal bootstrap equation, the only possibility that can that solve the conformal bootstrap equation is only blue region with edges, and somehow Ising model sits in. There is some kink here, and somehow Ising model sits in living in this kink. And the value they obtain is roughly 1.4 for energy density operator, and then for spin operator conformation 0.518. So those are the. And what's going to happen is that if you do the, I mean, how to say, if you move along these edges, you will encounter that at this kink, there's some operator will be the OP coefficient. Let's see. There's some operator C, sigma psi, operator coefficient becomes 0. So therefore, at this kink point, there exists only a primary field that is sigma and epsilon. So therefore, it becomes really minimum around here. So only sigma and epsilon. So the other part can have the other operator. So that's this kink. So this means that the kink, the position kink implies the minimum number of primary operator. And so that's what they obtained by using. It's a very surprising result. And then it consistent with Monte Carlo simulation. So even before this paper, there's some numerical simulation using Monte Carlo, and to get this how to say critical dimension. And they are consistent, in fact. You can apply the same method to the 2D Ising model. You just, instead of using Virasoro algebra, one can solve this conformal bootstrap equation to give the bound to the conformal dimension. And in fact, this is the result. And the kink again appear here, around 1, delta epsilon is equal to 1, and then here is 1.25. So therefore 1 over 8. So this is consistent to what we learned in this lecture. Okay. Again, it exists that the Ising model in the lives in the kink of this conformal bootstrap equation. Okay. Bound for this. So this means that implying this minimum number of primary operator at this kink. For the other places, it can accommodate other operator. If you do the 4D Ising model using the conformal bootstrap equation, there is no kink. It just goes like this. So this means that the fixed point for the Ising model is in fact a trivial fixed point, which means that the CFT is the really free CFT. So which means that if you do the Lagrangian description, Lagrangian is something like Lagrangian is 1/2 del mu phi. This is a free field Lagrangian. And in fact, in 4D, this is the only fixed point you can encounter. So this bound is only obtained by considering this 4-point function, sigma, 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 sigma. And they apply the Conformal Bootstrap equation only for this 4-point function. And then the second paper and so on, the subsequent papers, they consider the 3 kinds of 4-point functions. So here, as you can easily see, this sigma, 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 and also 2 sigma and 2 epsilon, and also the 4 epsilon. So these 4-point correlation function you consider and apply the Bootstrap equation again. And then give a bound. And surprisingly, so it gives you a lot more constraints on the OP coefficient. And then for 3D Ising model, you can just have this kind of constraint. So this blue region is allowed, and they call this one is island, and this one is called, oh my goodness, how to say in Chinese? No, in English? Continent. In Chinese, 大陆. Is that correct? Anyway, so it's a continent, and this is called island. It's called 岛. And then, you can solve the Bootstrap equation very, you just solve many higher orders. And in fact, the Bootstrap equation give you more restricted than the Monte Carlo simulation. So Monte Carlo simulation is something like can give like this kind of constraint, but the Bootstrap equation can narrow constraint. So the Bootstrap equation makes the island smaller. Okay, smaller. So therefore Bootstrap equation is much more efficient. Okay, so that's how they solve, and then the value here is the as follows. So the conformal dimension epsilon is 1.4 and so on, and the sigma is 0.51 blah blah blah. So this is the more precise how to say value than the Monte Carlo simulation can give. And moreover, so if you solve this 3 kinds of 4-point function, one can get the more OP data. Okay, so those data is just they're not these are epsilon sigma only primary field, and the other are the some other field, and T mu is also primary field. And then, and so on. So those are OP data. So these are conformal dimension, and the OP coefficients are given here, and so on. So those are the, conformal data, one can just give into the, using, by solving conformal Bootstrap equation. Okay. So just starting from this very simple idea, even though it's just the idea is given in like as further 70s by Polyakov and many people. I don't remember the name. And then people just do not use that idea. But if you use this conformal Bootstrap equation very cleverly, one can just really like how to say determine without like rely on anything else. Just using only this solving this Bootstrap equation. But of course, you have to use computer, and then to determine this conformal data of these 3D IC model. So this is one of a remarkable result by just solving this conformal Bootstrap, which just equation given here. Using conformal symmetry, one can solve the Ising model in 3D. So that's the I wanted to explain today. Unfortunately, fortunately, it's a bit maybe too fast. But anyway, so that's what I wanted to explain today. Okay, I think that's I wanted to explain for this lecture. And do you have any question? Yeah, I think it's a bit early, but I think it's okay. It's the last lecture, so yeah. So I think we just give there is a it's called what is it called? Student evaluation is called评价. Yeah. Just keep an honest opinion for this pincha, and then I can improve the the content. So this time this is actually third time to I taught 2 times Conformal theory unofficially, but this time I changed the topic a little bit, including the high dimensional Conformal theory. And then both it's understandable to you guys. Of course, the topic is a bit advanced, but yeah, high dimensional conformal field theory is also very important for in quantum field theory, especially those people working in the whatever particle physics, even or theoretical physics and so on. Not only 2D is important. I mean, 2D is also important, but high dimensional conformal field theory is also now like a kind of have some tool to analyze. That's what I wanted to. I want you to learn through this lecture. Okay, and the next week we will have an exam. As I mentioned, it's called Kaichuan. But only you cannot use the laptop, only like a tablet one without internet. And then please obey the rule. Otherwise, I have to give you F. Unfortunately, I don't want to give you F. So please obey the rule, and then please do not break the rule. So only you can read the PDF file for this one, and then download before the exam. Or the PDF file or whatever you want to watch, and you cannot type. You cannot whatever. I mean, if you type something, yeah. So that's it. And then, yeah. So 2/3 from 2D CFT, and 1/3 from high dimensional CFT, and then. Yeah, I mean, just don't worry so much. I mean, just to briefly review my lecture or like my lecture note, and that's enough. And then, yeah. Any question about the final exam or whatever? You cannot, you cannot search your PDF, word in PDF. And that's fair. I think that's fair, yeah. Yeah, because when you break some book, you cannot search word. You cannot search word, it's the same thing, yeah. I just don't want to like print out 100 pages of my lecture note or whatever lecture note and bring it to here. That's meaningless. It's a waste of paper. That's any other question? Yes. Yeah, so in my lecture note, I cited, as I mentioned, so Richkoff. So the most famous is this Richkoff. So one of this Richkoff and Simon is this is EP. I forgot EP blah blah L Simon Daffen. He's Caltech professor, so he has the like huge note by on Caltech courses. I don't remember. I cited in my lecture note. So in the Caltech course, also there's a shorter one for Tazi, and also Richkoff. I think Poland and Richkoff. Who else? There's the one is called recent. So really recent development. The slide I showed is the covered by Conformal Bootstrap blah blah numerical blah blah blah. I cited in my lecture note. I think my lecture note. And then yeah, I mean so my lecture note is heavily followed by Nakayama. My lecture note is heavily on Nakayama, written in Japanese, so you cannot access. But you can access my lecture note, so which means almost anyway. There's another lecture note Nakayama by scale invariance, scale versus conformal invariance, something like that. Conformal. That's also very nice one. Yeah. So just everything I think is decided in my lecture note. Or like my syllabus. Conformal versus scale invariant, something like that. Is there the no? I can send the link to the WeChat group. I can do it now actually. EFT. Okay. I think let me do it now with speech. Yeah, because I mean, when I prepare a lecture, I just heavily rely on these lecture notes. Yeah, EPFL. And then. Yeah, so yeah, BG. So this one is called Conformal Bootstrap. I mean, I can send those ones. Heavily, yeah. When I prepare a lecture, I heavily rely on those sources. That's why I just don't want to make my lecture note on public, because I mean it's just almost copy and paste. Yeah. So another Nakayama's one is this one. Okay, good. So these three, and Simon Duffin's one is if you search Google, Google or whatever, his website you can easily see in the GitHub and so on. Any other question? Yeah, I will put these slides into the what was that? E-learning, so that you can search the you can take a look, and then important thing is that those link the link paper I started you can, if you click it, you can just move to the original paper. So that the yeah. Any other questions? Okay, if not, let's finish this lecture, and then good luck on your exam. Okay. Yeah, so I put today's slides into the e-learning so that you can check it. And how can I log out this one? Oh, good. Okay, and then stop it.